in this video we are going to see Unit 6 by me, Forces and Motion, or Unit 5 in the book.
Then we're going to define what a force is. And a force is any cause. So force is a cause whose effects include either changes in an object's state of motion or deformation. For example, here, we're going to change the motion of this ball because it's just stopped, it doesn't move. And we're going to apply a force because we're going to push it, and it's going to change its state of motion because it's going to start moving. It was not moving, and after applying the force, it's going to start moving. It's going to start rolling. So that's a change of the state of motion, and the cause of this change is a force. Okay, the force that this guy is applying. And also we can deform objects. So here we have someone pinching a ball and deforming it. That is also caused by the force done with the fingers. Sometimes the two effects can occur simultaneously. So here we have example where it's only the change of the state of motion, and here's only the deformation. But imagine this is a real picture in Wimbledon. Just imagine what this ball goes through. I mean, they are like Nadal or any good tennis player. They hit the ball so hard that it deforms. It's going to change the state of motion because if it was moving this way, after hitting it with a racket, it's going to move the other way. So it's going to change the state of motion. But also, you can see it's totally deformed. So again, the two effects can occur simultaneously, like here, or not, as we saw in the previous examples. So that's a force. We measure the force in Newton, and the letter for Newton is N, because maybe you know Newton, the guy, Isaac Newton, was the guy that talked about forces and the laws that we are not going to see in this unit, but he formulated 3 laws, very important laws that apply even when you're at university about forces, and that's why the units have the name of this great scientist, Isaac Newton. So the unit is Newton, okay, capital N. And we say that forces are exerted or applied. Okay, we don't say that something has force or it's full of force or no. A force is applied or exerted. That's the scientific way of saying it, so please use it. And it's also important to know that a force is a vectorial magnitude. It means that to represent force, we use an arrow. Okay, so here, for example, I took it from this picture from a Spanish book. That's why everything is in Spanish, but I know you understand it perfectly. So when you pull the milk up, you need to, if you want to draw the force, you need to draw it in the direction on which you are applying this force. And in this case, it's upwards. And if you push it against the table, for example, then you're going to put the arrow going down. Or if you move it, you're going to draw the arrow in the direction that the force is applied. It can be, in this case, it's leftwards, it can be the other way around. Okay, that's about force, but forces help us to classify materials depending on the effects we see in them. So we're going to classify the materials in 3 types. So rigid material, elastic material, and plastic material. Let's see the first one. Rigid material, it's by definition, when we apply a force to this kind of material, it doesn't get deformed. Okay, so for example, if you can try to compress a stone, and not going to happen. This is not going to happen. It's not going to change the shape. The stone is going to maintain the shape. So that's why we say it's rigid. Okay, it's a rigid material. Also, you can apply a force with a hammer to a stone. It's not going to be deformed. It's not going to be deformed, right? Here you can always say, yeah, but if I do it really, really strongly, if you do it really, really strongly, you're going to break it. But it's not going to, it's different breaking something than deforming something. Because when you deform something, it's not breaking. But when you break it into pieces, that's, of course, it's going to change the shape, but because you just passed the breaking point of that material. Okay, so we are talking always of normal forces, not really, really strong ones, because if you, of course, if you use a very strong force, you're going to break it. We are not talking about those cases, just normal forces, okay? Next example, elastic material. When we apply a force to the material, it gets deformed. So it's different because the rigid one didn't get deformed. This one is going to get deformed, but when we stop applying the force, it's going to turn to the original shape. For example, here, the spring, we compress it, and that's because we are applying a force with hammer. But when we cease to apply this force, when we stop applying it, it's going to regain the original shape. Also with these air balloons, you have all played with these balloons, and they are very entertaining because you can jump with them. They are bouncing balls, and that's because you can compress it, doing force against it, but then they are going to regain the shape, and that's why they bounce back. Again, if you're like an animal and you apply a super strong force, you're going to not break it because this is elastic. I mean, of course, if you're applying a really strong force, you're going to break it too. But before breaking it, you may have the case that the elastic material can never return to the original shape, and that's because it has passed the elastic limit. So you have a limit when it's not elastic anymore. If you are too strong, I mean, if you apply a force that is very strong, and if it's even stronger, then we break it too. But again, we are talking about normal, common forces, nothing like you want to break something, okay? But if you do it, of course, you can break it or deform it permanently, etc. And the third example is third type of material is plastic material. And in this case, when we apply a force, it stays permanently deformed. And even if you stop the force, it's going to stay the same. For example, with clay, you can mold stuff because you press it, it takes the shape you want, and then you stop pressing, but it stays the same. So, and here, of course, you have all played with this, and you have seen that you can deform it very easily and create the forms you want, and then it stays the same. So that's a plastic material. But we're going to classify, so we have classified the materials according to the forces, but now we're going to classify the forces. And we have two types, contact forces and non-contact forces. And contact forces, that's very easy because the name says what they are, and contact is necessary for them to act. For example, when we're playing billiard and or pool, the Americans say pool, we need to touch the ball so that it moves. So it's really contact. So when we want to move the milk, again, we need to touch it. When we are playing sports and we want the ball to move, of course, we need to kick it or hit it. And here with we are going to apply the force with the string here. So because otherwise it doesn't fly. we cannot control it, and we control it, and we exert the force with the tension that is in the string. So we have some forces that are contact forces, where we need something touching for them to work, and we have other kind of forces that are called non-contact forces or forces at a distance. The scientific name is field forces. The field is campo, but it's a concept a bit complicated. But this is the real name, okay? Field forces. I'm going to call them probably non-contact forces or forces at a distance because it's easily understood. But this is the real name, field forces. And of course, if we call them non-contact forces, it's because contact is not necessary for them. And you know one of them, for example, the gravitational force. You know, planets, for example, the Earth attracts the Moon, and that's why the Moon rotates around the Earth, and the Sun attracts the Earth, and that's why the Earth rotates around the Sun, but they are not touching each other. So the gravitational force, you don't need contact for the gravitational force to work. Here we have someone jumping, and it's going to fall down because the Earth is attracting this person. And again, the Earth is not touching the surface of the Earth, but he's feeling the attraction of the Earth. And here is a very small example, but it's real true. It's true because here also you can see the gravitational force. The oil is falling down because it's also feeling the attraction of the Earth, and it's not touching the Earth. You can see it. So it's a non-contact force, the gravitational force. You all know this one because you feel it every day. You feel it so much you have forgotten it exists because you think that's a normal thing to have. And no, it's because you're on Earth. If you were in space, you wouldn't think this is normal. Okay, so another example, the electromagnetic force. And this is based on charges. So the gravitational force is based on masses. This is based on charges and is the one that repels or attracts charges and magnets. So here we have a magnet levitating, and this is because we have here another magnet and they are repelling. And they are repelling so much that it floats over this other magnet. And here we have, I don't know if you have done this experiment, but if you wrap a balloon against something made out of wool, it's going to get charged, and then you can repel another balloon because they are going to change if you charge them, both of them, you're going to charge them with the same charges. For example, negative charges and negative charges. So if you try to approach them, they are going to repel. So again, this and they don't touch, but they feel the repulsion or the attraction. If you use, for one, I think is amber, but you maybe not have that in hand. You can charge them positively or negatively using different materials. But if you use the same material for two balloons, then they are going to repel, and they are not touching. They don't need to feel the contact to feel the force. That's why, again, these are non-contact forces. These are very important, and we are going to work more, especially with the gravitational force. But it's important for you to know that there are other forces, like the nuclear one. This is the one involved in phenomena such as radioactivity. This is, for example, the X-rays. When you need to get an X-ray of your bones or something, you use radioactive materials. And what is happening here is that the nucleus of something decomposes, okay? And the radiation that you get, that's the one that you use for the X-rays. So X-rays are, I think, this kind of this one, like the gamma, but yeah. Anyway, so the nuclear energy is the nuclear force is the one that keeps the nucleus of the atoms together. So all of these protons and neutrons, they are together because they have a nuclear force holding them together. So, because, I mean, you can guess, here we have a lot of protons, and why they don't repel each other? Because they have this nuclear force that is much greater than the electromagnetic force, and that's why because this is greater, it overcomes the electromagnetic force, and even if they are all positive, they are staying together because of this nuclear force. And here is the video for today, and the last video before the holidays, but you need to do these exercises for Thursday. And after Easter, we'll have all the videos and we will keep on working. I think you have worked really well, most of you anyways, and you deserve to have holidays. So yeah, that's going to be it. If you haven't done the elements presentation, you should prepare it because we're going to do it after Easter. If we are back into the classrooms, we will do it in the classroom, otherwise you will do it online as I do it. So please prepare your presentations for the 11th, because I mean the 11th I think is the last day, but the 12th you're going to present either in class or here in video conference. So please, you can do it this week so that you don't have to work during Easter, but have it. And that's all. I hope you have a great week, and I'll see you in a video conference. Bye.